Hey guys, in this WACE Academy lesson, we'll be looking at two-way frequency tables, which is covered by dot points 3.1.2 up to 3.1.4. Two-way frequency tables are a method of sorting statistical data in terms of two variables, where the rows of the table indicate the first variable and the columns indicate the second variable. This generic two-way frequency table shows where the two variables are located and where the data is entered. If we were trying to find the frequency of results that matched y of variable 1 and green of variable 2, we'd locate the cell that is in the intersection of these two categories. So in this case, the value would be 3. Let's say we collected data on the popularity of each gender for two different sports offered at a school. There are two sports offered, basketball and tennis. We'll put the different sport categories as the rows and the genders of students as the columns. Now we can place the frequency of each student participation in each cell. On the tennis team, there were 20 females and 35 males, and on the basketball team, there were 18 females and 28 males. Now let's say we wanted to find the percentage of males and females in each sport. To do this, we'll first have to create some totals we can base the percentages off. We'll add up the number of males and females playing each basketball and tennis to find a total of students playing each sport. Using the percentage formula, part over the whole multiplied by 100, we can turn these frequencies into percentages, rounding to the nearest 1%. 35 of 63 is 56%. 28 of 63 is 44%. 20 of 38 is 53%. And finally, 18 of 38 is 47%. If we add up these percentages, we can confirm the totals of the columns are 100%. Now it's easier to pull off some quick stats from the data. There was nearly a 50-50 split for which sport a specific gender would play. A male student is slightly more likely to pick tennis over basketball, as 56% of males played tennis compared to 44% who played basketball. Similarly, this is true for females, with again just 6% more of the female sample playing tennis. Another way of presenting the data, similar to percentages, is as proportions. Repeat the same process by creating the totals of the necessary category, then divide the frequency of the cell by the total. The only difference from percentages is you don't multiply by 100, so the proportion total will be 1 instead of 100. Let's do this again for the same data. Rounding to the nearest one decimal place, 35 of 63 is 0.6, 28 of 63 is 0.4, 20 of 38 is 0.5, and 18 of 38 is 0.5 as well. Note the reason that the last two results both equaled 0.5, even though they weren't equal results, is because we rounded to the one decimal place. If we rounded to a greater number of decimal places, then we'd see the difference. Similarly, the total of each column will be 1. Let's say a fisherman recorded the colour and length of all the fish he caught. The fish were either blue, green or grey, and their length was either between 0 and 20 centimetres or 20 and 40 centimetres. This time we're going to find the row totals and then what portion of the length categories each colour was. This wording may take a bit of effort to understand, but imagine the two length categories, 0 to 20 centimetres and 20 to 40 centimetres, are two different pies, and we've cut both of these pies into 3 unequal slices. Each slice now represents which colour the fish can be. The bigger the slice, the more fish caught of that colour. Now to calculate the portion, we'll divide each cell by their row total, or, referring back to our pies, we'll compare the size of each slice to the size of the whole pie, or the row totals. 2 divided by 14 is 0.143, which we'll round to 0.14. 4 divided by 14 is 0.286, which will round to 0.29. We'll continue this process until all the cells are filled. For the second row, we'll use 15 as the total. Something else we can be asked to do is to find the ratios of two particular results, or one specific result to an entire category. This data displays the results from a survey asking men and women what their favourite method of transport was to work. We are given a question: find the ratio of the number of females who caught the bus to the total number of females surveyed. To answer this, we would find the cell that represents both the female category and those who used a bus, which is this cell, so 6, as well as the total females surveyed, found at the bottom of the female column, so 57. Now we know the ratio of the number of females who caught the bus to the total number of females surveyed is 6 to 57. You may have noticed that in some circumstances, the data we have used has some sort of association between the variables. In other words, we can observe a pattern that occurs in the data between variables. As one variable increases, the other may increase as well, or as one increases, the other may decrease. This data comes from an investigation to find the number of languages spoken by individuals and their current salary from a sample of employees. Upon a quick scan of the data, you'll notice there are two areas of high frequency: those who spoke 1 to 2 languages and earned up to $75,000, and those who spoke 3 to 4 languages and $100,000 plus. This is one possible example of an association. In this case, the more languages an individual could speak, the higher their salary was. Let's change these results to percentages to see of each salary level which number of languages studied were the most popular. So we want the row totals to equal 100%. In other words, the rows are our pies and the slices will be each cell in the rows. We'll round to the nearest whole percent. From here we can see 48%, nearly half of those who earned less than $50,000 spoke one language, as is the same with those earning $125,000 plus that could speak 4 languages, which displays even further the association between high salaries and more languages known. A practical application of this data could be encouraging people to learn multiple languages if they want higher salaries. Note that some of the totals may not actually add up to 100% due to the rounding off. This brings us to an important note. There doesn't necessarily need to be a cause and effect relationship for there to be an association. An association is only a pattern between two variables. In this case, it is likely that knowing more languages caused people to be in high demand and thus earn a higher salary. But we need to be careful. This doesn't mean that if someone pays me a salary upward of $125,000 that I'll magically know how to speak Chinese, French, German, and English. A more common example of association would be the sales of ice creams and the temperature of the day. With hotter days, more ice creams are probably sold. So, as the recorded temperature increases, so too does the number of ice creams sold from an ice cream truck parked near a beach. However, with colder days, less ice creams are sold. So because both variables temperature and ice creams sold increase and decrease with each other, this is called a positive association. You may have noticed that when we use percentages and proportions to represent our data, some misleading figures came up. It's important to remember when dealing with your percentages and proportions that they are always in comparison to something. Looking at our first example, it is clear looking at the raw data that males make up most of the students enrolled in each sport, as well as the total amount of students surveyed. But looking at the second table, where we have calculated the percentage of which each sport each specific gender plays, we've essentially separated the male and female results, and we make no comparison between genders in this table. Because all the percentages on the table are roughly 50%, it is possible this data can appear to imply that there are roughly equal number of males and females surveyed. However, we know this isn't true, but the reason it looks like this is because we calculated the percentages using different values as the total, or the denominator. So we can't directly compare the percentages across genders, only the percentages within the same gender category. The 53% of females playing tennis use 38 as the total, seen as the denominator, while the 56% of males playing tennis use 63 as a total, again seen as a denominator. Now we've finished the theory, let's apply it to an exam question you could expect to see in WACE exams. Lucy surveyed 30 students randomly selected from her school to investigate how many students spoke a second language and if they played a sport outside of school. She found 7 students spoke a second language and played an external sport, 7 students spoke a second language but didn't play an external sport, 6 didn't speak a second language and played a school sport, and finally, 10 neither spoke a second language nor played a sport outside of school. The first part asks us to organise the data she gathered into a two-way frequency table. First, we'll draw our table up It should have enough columns for the two possible options of the first variable, and enough rows for the two possible options of the second variable, and finally 4 cells where we can enter the data. Next, we'll come up with some suitable titles for our categories. Referring to the question, a good set of titles would be spoke a second language, didn't speak a second language, and played a sport outside of school and didn't play a sport outside of school. Finally, take the values from the question given to us and place them in the correct cell. Be careful each value goes in the correct cell here, you don't want to lose marks. The next two parts are asking us to calculate percentages. Part 2 requires us to find two values before we can calculate the percentage. All students surveyed, and the number of those that spoke a second language but did not play a sport outside of school. The equation we'll use is the general percentage formula, part over the whole times by 100. Then we'll put in our own values which we've just found. So, the whole will be all students surveyed, 30, and the part will be all the students that spoke a second language but did not play a sport outside of school, so 7, then multiply by 100. And so our answer is 23.3% recurring, which will round to 23%. The only difference with part 3 are the values used. For this, we'll divide the number of students that didn't speak a second language but did play a sport, 6, by the total number of students that didn't speak a second language, 6 plus 10, 16, and then multiply by 100, which rounded to the nearest whole gives us 38%. Notice parts 2 and 3 each have different ways of telling us which total to use. The first question says, what percentage from all students surveyed, whereas in the third part, it says, out of all the students that didn't speak a second language. Getting familiar with this sort of wording is key to answering these questions. I hope you enjoyed this lesson. If there's anything you had trouble with, please leave a comment letting us know about it. See you next lesson, where we'll be going a bit deeper into the associations that can occur within data.